Okay, so today we're going to start talking about aberrations. We're going to start with spherical aberrations. But first, let's talk a bit why aberrations occur. Up until now, when we've been designing our optical systems, we only cared about the combination of radii and index of refraction insofar as they gave us the, the, the focal length that we wanted, right? But the truth is that the combination of radii on our lens or the index of refraction matters a lot because refraction is nonlinear. So let's put that in this little box here. Now what nonlinear means is that, for example, remember Snell's law, it says n1 sine theta 1 is equal to n2 sine theta 2. If we were to double sine 1, or sorry, double theta 1, so theta 1 is equal to, theta 1 prime, let's say, is equal to 2 times theta 1, what happens to theta 2? Is theta 2 doubled as well? And the answer is no, right? For small angles, yes, it is pretty close to doubled, but for large angles, it's absolutely not doubled. So it's not the case that theta 2 prime is equal to 2 times theta 2. It's not the case. And this is why aberrations occur, because if we double the angle, so if we have a lens here, let's say, and we have a ray that is coming at it like this, and then we double the angle here, they're not going to be refracted parallel because they're not going to, the change in angle is not going to be the same. Even though we've doubled the angle from here to here, right? And so the consequence is that we have to choose R2, R1, our index of refraction, our focal lengths, and our lens positions. You have to choose all those in order to minimize our aberrations. So that's one reason why why aberrations occur. The other one is that spherical surfaces are not the ideal surfaces to focus a point source of light. And here's where you guys can remember that active learning we talked about at the very beginning of the semester. Rephrase this I'm going to write it down, but rephrase it in your own words. But spherical surfaces are not the ideal surface for focusing light. Which makes you ask maybe why do we use spherical surfaces? And it turns out they're just really easy to make. If you take two flat pieces of glass with some polishing compound between them and start moving them, I'm not exactly sure how, but you can do this on your own. You can actually create two really well-defined spherical surfaces. In fact, you can grind your own lenses for making telescopes and stuff like that at home. People do it all the time. So they're easy to make, which makes them cheap, and it's very expensive to grind non-spherical surfaces because you have to have basically a really high precision CNC machine with a really good surface finish, and that's just expensive. And we'll talk about that after we finish talking about aberrations. We'll start talking about what you can do in terms of buying stock lenses, which means lenses from companies, in order to minimize aberrations. All right, so the first aberration we're going to talk about is spherical aberration. We've already seen this in action because when you guys have done ray tracing on your designs, the rays never all meet at the same point when you want them to, right? If you think back to the second design we did where you're supposed to create the ray gun, the blue rays, the outside rays that you were trying to focus to a point, for a lot of you guys focused much more closely to the lens. So they had a much shorter focal length than the rays that were close to the optical axis. Those had a focal length that was much closer to 10 feet, which is what you wanted. So the effect of spherical aberration is exactly that. It causes the focal length to vary as a function of the distance of the ray from the optical axis. Okay. And so as a result, spherical aberration, or SA, is proportional to the diameter of the beam to the fourth power. So, wow, that's huge, right? How many times in your life do you ever see things that are to the fourth power? I think radiative heat transfer is it to the third or fourth power? It might be to the fourth power. But fourth power is huge. That means if you double your diameter of your beam, oh shoot, this mental math's not easy. So it goes 4, 8, 16, 32 times worse spherical aberration, right? It's also proportional to 1 over the focal length to the third power, right? So here too, if you have a short focal length, right? If you have a short focal length, it's on the bottom and raised to the third power. So here it'll be what? 16. So if you have your focal length, you'll increase spherical aberration 16 times. And so the consequence is that it grows incredibly rapidly as F number gets smaller. And this is why we looked at low F number lenses in our class time like a week ago, I think. And we saw that well, it seemed like a modest decrease in F number increased the cost of a lens from somewhere between $600 and $800 to $12,000. And the reason is it requires lots more lenses and lots more precision in order to minimize aberrations as you increase your F number. Because remember, F number is equal to F over D, right? So increasing D and decreasing F is how we decrease our F number, which is what we want to do usually. And both of those are bad for spherical aberration. Cool. So let's go to the next page here. This is an example of how spherical aberration can affect an image. We have the same image here, but we've changed their F number. If you look, here's our F number on the left-hand side is 1 over 2. And our F number on the right-hand side is 1 over 8. And you can actually see that the image is clearer on the right-hand side. And the reason the image is clearer on the right-hand side, if you compare these O's, these zeros, the reason it's clear is because we have less spherical aberration because our F number is higher, which means either our focal length is higher or our diameter is smaller, right? And in reality, what they did is they just changed the diameter. So there are, for a thin lens, right? For a thin lens, there are analytical expressions for the amount of spherical aberration that we have. And here's one equation. I'm not going to ask you guys to learn it or memorize it or even look at it past this moment. I just want you to know that they exist. But what's nice is we could take the derivative of this with respect to properties we care about. Like if we substitute in this sigma here is the ratio of R1 plus R2 over R2 minus R1. This is called the shape factor. And P is the ratio of the S prime minus S over S prime plus S. And this is the image minus the object over the object plus the image distance. They use a little different notation here for this equation. So what we can do is we can actually take the derivative of this equation with respect to P and with respect to sigma, and we can find out where it's 0, and that's where we minimize our spherical aberration. And so you can see actually here is a here we have they don't say what the focal length is, but let's call it just a basic thin lens or basic lens, and we change the shape factor. On the left hand side we have a -2, and what we see is we have a meniscus lens on this side. on the right-hand side, we have a +2, and it's the same meniscus lens, just flipped in direction, right? Because what we're doing is we're just changing the sign on sigma. So we're changing the order of R1 and R2. And the minimum occurs somewhere in between. And here the shape factor occurs, the minimum occurs about 0.5. And this is what's called a best form lens. Now remember that term, because we're going to talk about that term when we go to optical component suppliers' websites and we see what kind of lenses they sell. They sell lenses that are quote unquote best form, right? Now, what's important to know is that this is best form for a given P. And remember, P is a ratio of our object and image distances. So if we change the distance of our object from our lens, we're going to change P, which means we change our best form. And so what people have done is they've basically said, okay, let's just assume that one of our objects is always going to be at infinity. Okay? So if one of our objects is always at infinity, P is equal to 0. And then we can sell a best form for that given P. Although if you wanted to, you could solve for sigma min that minimizes as a function of P. So we can solve for the form shape factor that for a given P minimizes this equation, and that is equal to -2 n squared minus 1 over n plus 2 times P. Although you'll never use this because you'll never make a lens on your own, right? What people do is they'll sell you best form lenses, but they're assuming a P is equal to 0, which tells you that one of the objects or the image is at infinity, right? Cool. Okay, so rules of thumb for minimizing spherical aberration, though. Oftentimes you don't have a lot of control over your focal length, right? Although we can try this. So hold on, we can say that smaller diameter of your beam equals smaller spherical aberration, as well as longer focal lengths. And we'll see in a second how longer focal lengths come into play. You might think like we don't have a lot of control over focal lengths, but we actually do have a lot of control over focal lengths. All right, so 2, and we can orient the lenses so that we keep. This is a good time to rephrase this. So wait until I finish the sentence and then write it in your own way. We keep incoming and exiting angles with respect to the normal as equal as possible. And what this does when we do that is that effectively minimizes the maximum angle that our rays have to make with a surface. And if we're minimizing the maximum angle our rays have to make with a surface, then we are, if we scroll back up to here, remember this equation becomes increasingly nonlinear the larger θ1 gets. So if we can keep our angle small, we keep the nonlinearity down, which means we keep our aberrations down, right? And we can see how that works here when we look at some lens systems. If we continue to scroll down, oh, sorry, there's one more rule here. We choose lens combinations that result in the smallest incident and exit angles. Okay, so if we look here, so this is an example of doing a lens where we have a parallel beam coming into the curved side and leaving out the flat side. So this is a plano-convex lens. If we look at this, and we'll look at this in more detail with the ray tracing, if we flip it, what we see is that the angle for the incoming side is going to be hitting the flat side, which means its angle is effectively 0, and it leaves at a high angle, and so that's bad. What we want is we want to match these angles here, this angle here, and this angle here as much as possible. Okay. So if we try to apply these rules, here's an example where we have the same focal length, and we try to minimize aberration. So we take one single lens, plano-convex, oriented in the best possible direction. And we see that we have a lot of what they call transverse aberration. So transverse aberration is the amount of aberration that occurs in this direction. So at the focal plane, how much variation is there in height for the rays when they hit the focal plane. We can also describe it in terms of longitudinal aberration, which is basically the variation in focal length, which is what is plotted here. So there's two different ways that this is plotted. Transverse aberration, yeah. If we take two lenses, so that if you look, the angle for each of these lenses is smaller, right? Each time it enters and exits, it's smaller than the net angle here. We can decrease it, actually, the amount of aberration by quite a bit. If we look at the greatest part here, we're at least, what, a factor of 3 smaller? Oh, it's a quarter improvement. Yeah, there you go. So it's a factor of 4. And then we can use our improved shape factor, right? So in each of these cases, we can choose our best form lens. In this case, it's a best form and a second best form. Combine the two, and we can decrease the aberrations by a factor of 2. And if we keep this game up, we can add another lens. Again, each time reducing the angle that the rays hit or enter and leave the lens. We get another improvement by a factor of 4. So if you're keeping track here, we have a factor of 4, 8, 32, right? Add another lens, and we have a huge increase in improvement of our aberrations. And this is why, if you go ahead and look this up. Let me make sure when I tell you the Google term that it works, but optical design of lithography. Let's see, and then do a Google search of it, and then do an image search. And oh yeah, there we go. You'll see some absolutely insane systems. So like I said, you Google the optical design of lithography systems, and then go switch to a image search. There's just an insane number of lenses. You'll see some with on the order of 20 lenses, and each one of those has to be aligned and spaced correctly. But the whole goal is you're alternating your index of refraction to minimize chromatic aberration. You're using whole sets of lenses where you do exactly what we were talking about here with this thing, where you add multiple lenses. And actually, why don't I just share my screen really quick so you guys can see this at the same time. So let me share, stop, and then I will share my screen here. So again, we're searching the optical design of lithography systems, and this is an example of actually it's a student optical design competition. So they chose just an insane number of lenses, right? And the whole goal is to produce a magnification where we take points on this left-hand side, and we reduce the magnification so that they're much smaller on the right-hand side. And this is what the whole lithography systems try to do, right? They try to create microchips which have a large pattern that they try to reduce down to a small pattern very accurately with minimal aberrations. There are some really insane patents out there where you can look at some of these systems. Here's another one which looks pretty similar, because the methods used to reduce aberrations are fairly similar, right? We'll talk about this at the very end, at the end of this series of lectures. Okay, so let's look how this looks like using our ray tracing system. So here I've, and I'll post this to our, oh, did I manage to share that? I didn't. Hold on, share. There we go. I'll post this to UB Learns, but here we're going to look at spherical aberration. We're going to load a lens. And the lens we're going to load is a 100 millimeter plano convex that's 2 millimeters in diameter, or sorry, 2 inches in diameter. So it's a large lens, right? And as we know, the farther we get away from the optical axis, the more aberration we're going to get. And so here we've oriented the lens in the wrong direction, right? So remember, we always want to orient a lens so that the incoming angle and exiting angle are as equal as possible. And here we can see that the incoming angle is 0 with the normal and the exiting angle is quite large. And so these are not equal at all. And as a result, we have pretty high spherical aberration. If we zoom in on the region of the focal region, you can see that the red rays converge right around what, 258 roughly, and the blue rays converge at 228, right? So we've got 30 millimeters of change in focal length, which is incredible. It's a huge number, right? This is strong, positive spherical aberration. And we'll talk about how we measure the spherical aberration, but one way is through what we call longitudinal aberration, which is the change in this focal length, right? And so you would plot over, as a function of the distance of the ray from the optical axis, you would plot its focal length here. Anyway, we can talk about that later though. Then if we flip the lens, all we did was change its orientation. Now you can see that it enters at an angle that is not equal to 0 and exits at an angle, again, that's lower than what it exited before. You can see we greatly reduced the amount of aberration. So let's go scroll up and compare these two really quick. So you look at that one, and you scroll up here, it's like night and day, right? And so if we scroll in on here, we see that the change in focal length is much, much different. So now our red rays meet about, I don't know, 253 maybe, and the blue rays meet around 245 roughly. So we've reduced it from 30 millimeters down to 8, right? Which is a huge change just by flipping our lens, right? Great. So if we zoom in on here, right, this is the correct orientation of the lens. We have the curved side facing the object at infinity, and we can see that the angle that the ray makes with the surface of the front and the back is not equal, right? It's not equal, but it's closer to equal than if we have it this way, where with the angle that the ray exits is quite large, and that large angle that it exits relative to the surface is subject to that nonlinearity that refraction has, and that is what's causing our aberration. Cool. So if we come back to our lecture then, back to our lecture notes, I want to talk about, so here we can see exactly what I was talking about, where we plot the focal length as a function of the height from the optical axis of our rays. So height is in this direction, focal length is in this direction. And we can see that when we orient our lens convex plano, so curved side facing the object at infinity, the variation in focal length is much smaller than the variation of focal length when we flip our lens. So it's super important to orient your lenses in the correct direction. Oftentimes when you're building an optical system and you're having a lot of aberrations, the first thing you should check is simply, did I orient my lenses correctly? We'll talk at the end of this series of lectures about lens design paradigms that you can use to minimize aberrations. All right, now the next one aberration we're going to talk about is coma.